Welcome on to the online lecture series on applied electromagnetic theory. In this lecture, I'll be dealing with the topics from Module 3, and this is the Part 2 of Module 3. Myself, Rinju Mariam Raleigh, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. So, main topic that we are going to cover in this particular lecture is polarization of electromagnetic wave, or specifically polarization of transverse electromagnetic wave. And there are three types, that will be linear polarization, circular polarization and elliptical polarization. So here also we need the basics of vector calculus. All the theory that we have learned in the previous classes is needed in order to understand this particular lecture. So let's begin. What is a transverse electromagnetic wave? We already know a transverse electromagnetic wave, it is the electromagnetic wave in which both the electric field and magnetic field are normal to the direction of wave propagation. That means electromagnetic wave that has got no electric or magnetic field components along the direction of wave propagation. Direction in which the electric field point is called polarization of a transverse electromagnetic wave. Or we can also define wave polarization as the electric field vector orientation as a function of time at a fixed point in space. So this figure is a pictorial representation of a transverse electromagnetic wave in which the wave is propagating along z direction, electric field is along x direction and magnetic field is along y direction. So the direction in which the electric field point is called polarization, and that is our subject of interest for this particular lecture. Now let's move on to the depth of polarization. So what is the polarization of electromagnetic wave? It is the locus of the tip of the electric field at a given point as a function of time. That means the polarization is defined as the locus of the tip of the electric field vector at a given point as a function of time. Or in other words, we can say polarization is same as the orientation of electric field as a function of time at a given point in space. So any polarization state can be described in terms of mutually perpendicular components of the electric field and their relative phasing. That means suppose if the electric field vector is something like this, this electric field vector can be notated with the help of its mutually perpendicular components. So let's consider the electric field intensity vector. So the electric field intensity vector in terms of its mutually perpendicular components are given as Ez, t is equal to Ex0 cos omega t minus beta z Ax plus Ey0 cos omega t minus beta z plus 5p Ay volt per meter. Here 5p represents the phase difference between the electric field in x and y direction. And here we already said we are assuming that the wave is propagating along positive z direction. That is why we have got this minus beta z in this electric field expression. Now, polarization is, that is the orientation of electric field as a function of time at a given point in space. So let's fix that point in space as z equal to 0. So let's compute what is the electric field at z equal to 0. That is, general representation is E of z comma t. When z equal to 0, we can write it as E of 0 comma t. That is equal to Ex0 cos omega t Ax. Here it was omega t minus beta z. Since z is equal to 0, we have only cos omega t. That is cos omega t Ax plus Ey0 cos omega t plus 5p Ay volt per meter. Here Ax represent, that is the direction of this x component, and Ay represent, that is a unit vector for this y component. So depending upon the relative amplitude of the electric field in x and y direction, that is depending upon the amplitude of Ex0, Ey0 and the phase difference between them, that is a 5p, this polarization can be classified as linear polarization, circular polarization and elliptical polarization. So now let's see what is linear polarization. A wave is said to be linearly polarized if the electric field vector travels in a straight line with variation in time, or if the tip of the electric field vector, if it defines a straight line, if the locus of the tip of the electric field vector, if it defines a straight line, we call it as linear polarization. So we know the general expression for the electric field vector is given as E of z comma t, that is equal to Ex0 cos omega t minus beta z x cap plus Ey0 cos omega t minus beta z plus phi p ay cap. Now, for the wave to have this linear polarization, there is one condition, that is a phase difference between the x and y components, that phi p, that should be equal to plus or minus n pi, that is n equal to 0, 1, etc. So let's consider the case where n is equal to 0. When n is equal to 0, what is this phi p going to be? Yes, it is plus or minus 0 into pi. That means phi p is 0. So first we are going to consider the case n equal to 0. So when n equal to 0, we have phi p equal to 0. So from this particular expression of the electric field intensity vector, let's substitute phi p is equal to 0, and we are going to assume a fixed point in space, and that fixed point is z equal to 0. So E of 0 comma t is equal to Ex0 cos omega t ax cap plus Ey0 cos omega t ay volt per meter. So here phi p is 0 and there is no beta z term because we are considering the fixed point z equal to 0. So this is the electric field vector at z equal to 0 when the phase difference phi p is equal to 0. Now let's see what is the locus that is defined by this particular electric field vector. So for that, let's consider the different time instants. So it's clear from this particular expression that electric field, it is a function of time. So let's consider the different time instants starting from t equal to 0 till the time period of the electromagnetic wave. So when t is equal to 0, what is omega t? What is omega t? Omega is 2 pi by capital T into the time t. So when small t, that is a time variable t is equal to 0, you get omega t is equal to 0. When omega t is 0, just substitute omega t is equal to 0 in this particular electric field expression. What you will get? It is going to be Ex0 cos 0 ax plus Ey0 cos 0 ay. Cos 0 is 1, so we will get it as Ex0 ax cap plus Ey0 ay cap. So here this ax and ay, that actually represents the unit vectors. They actually represent unit vectors. Now let's consider another time instant, that is t is equal to capital T by 8. So I'm repeating again here, capital T represents the time period. That means at that, when t is equal to capital T by 8, omega t is going to be pi by 4. So omega t pi by 4, that means it's 45 degree. So substituting here omega t pi by 4, you will get electric field E0 comma t as Ex0 by root 2 x cap plus Ey0 by root 2 ay cap. So now I want to pause at this particular point. When t equal to 0, what was the magnitude of the electric field? It is Ex0 ax plus Ey0 ay. So let's try to plot it in the graph. We have x component, okay, so that we have this x direction and we have the y direction marked by y. When t is equal to 0, what is the value of electric field? Ex0. That means along x direction the magnitude was Ex0 and along y direction the magnitude is Ey0. So what is the point it defines? It is this particular point. So they have written it as t is equal to 0. So at t is equal to 0, it is Ex0 ax plus Ey0 ay, and this is the point it defines. Okay, this is the point that it defined. And when t is equal to 8, the value was Ex by root 2 ax plus Ey0 by root 2 ay. So that's going to be Ex0 by root 2 along x direction and Ey0 by root 2 along y direction. So that point is going to be somewhere here. Similarly, we can consider different time instants. If t is equal to, when time T is equal to T by 4, omega T will be pi by 2, and we know cos pi by 2 is 0, so the electric field value is going to be 0. So at T is equal to T by 4, its value is going to be 0. Okay. Then when T is equal to capital T by 2, that is half of the time period, omega T is going to be pi. So cos pi is minus 1. So substituting here, you will get electric field value as minus Ex0Ax minus Ey0Ay. So what does it mean? Along x direction, okay, its magnitude is minus Ex0, or you can call it as in minus x direction the magnitude is Ex0, and in minus y direction the magnitude is Ey0. So I'm writing it as along x it is minus Ex0 and along y it is minus Ey0. So what is that point it defines? It is this particular point. So consider another time instant, that is capital T, that completing one time period. So it is omega T will be 2 pi, and you will get the electric field value as Ex0Ax plus Ey0Ay. So that means it is again this particular point. So when we considered one complete cycle of the wave, we understood the tip of the electric field vector, it actually defined a straight line. The locus, it actually defined a straight line. So that's why this is called as linear polarization. That is, the locus that is defined by the tip of the electric field vector, it actually looked like a straight line. So we call it as linear polarization. And the condition that should be satisfied is phi p must be equal to plus or minus n pi. And here, how much is the angle of inclination? How much is the angle of inclination with respect to this horizontal axis? So that is, so let's say that angle of inclination as theta. So in terms of Ey0 and Ex0, we can write theta is equal to tan inverse Ey0 by Ex0. So if there is only x or y component present for this particular case, since here x is the horizontal axis and y is the vertical axis, and if the electric field, if it contains only x component, then we can call it as horizontally polarized, and if the electric field contains only y components, then we can call it as vertically polarized. So this I am talking with respect to this particular figure. Here the reference horizontal plane, that was the reference horizontal plane was x and the vertical plane was y. Suppose if this axis is different, then similarly we have to call it. And when just now we computed n equal to 0, what if n is equal to 1? Okay, if n is equal to 1, we know the general expression for electric field is Ex0 cos omega t minus beta z Ax cap plus Ey0 cos omega t minus beta z plus phi p Ay volt per meter. Substituting here, phi p is equal to 1. Phi p is equal to 1. So you will get, if n is equal to 1, you will get the answer as E of z 0 comma t is equal to Ex0 cos omega t minus beta z Ax minus Ey0 cos omega t minus beta z Ay cap. So here also you can substitute for different time instance. Okay, you can substitute for t equal to 0. Similarly, you can continue. But just take the first case. Suppose if omega t is 0, cos 0 is going to be 1. And here also omega t is 0, that means cos 0 is going to be 1. So what will be that particular point? What will be that particular point? It is going to be Ex0, it's going to be Ex0 Ax minus Ey0 Ay. So where will be that particular point defined in this particular graph? It means along x direction it is Ex, but along y direction it is going to be minus Ey0. So similarly, if you plot it for different time instance, you will get to know that if n is equal to 1, 3, 5, the electric field vector, it will move in second and fourth quadrant. That means if n is equal to 1, 3, 5, then the electric field vector, it will move in second, that is, this is the second one, second and fourth quadrant. Whereas if n is equal to 0, 2, 4, etc., the electric field vector will move in the first and third quadrant. So next category is circular polarization. Right now what we have seen was linear polarization. Another classification is circular polarization. So a wave is said to be circularly polarized if the electric field vector travels along a circle with respect to time. So as the time goes, if the tip of the electric field vector, if it defines a sort of circle, then we call it as circular polarization. And the condition for circularly polarized wave is Ex0 must be equal to Ey0 and that should be equal to E0. That means the x component and y component, their amplitudes must be same. And the phase difference between them, that should be odd multiples of pi by 2. So now let's consider this particular case. So for that, I'm taking the general expression of electric field vector, that is E of z comma t is equal to Ex0 cos omega t minus beta z Ax plus Ey0 cos omega t minus beta z plus phi p Ay cap. So here phi p is the phase difference and wave is propagating along z direction. So let's take the first case, putting n equal to 0, phase difference, it is plus or minus 2n plus 1 into pi by 2. So let's take when n equal to 0, phi p will be pi by 2. And electric polarization means that is the orientation of the electric field vector at a fixed point in space. So here also I am considering the fixed point as z equal to 0. So E of 0 comma t is equal to, what is Ex0? We already said that's going to be one amplitude E0. So let's say it is E0 cos omega t, because there is no minus beta z term, as we already assumed z equal to 0. So it is E0 cos omega t Ax cap minus E0 sine omega t. So why it is minus sign? Because here it is going to be cos omega t plus pi by 2. So cos omega t plus pi by 2, it is minus sine omega t. So that we substituted here. So let's say this E0 cos omega t is Ex and minus E0 sine omega t as Ey. Then this particular expression we can simply write it as Exax plus Eyay. And if you compute from this particular expression, that is Ex square plus Ey square, if you compute Ex square plus Ey square, you will get the answer as E0 square. It is very easy to understand. It is E0 square cos square omega t plus minus E0 square to sine square omega t. So that will be going to be E0 square cos square omega t plus sine square omega t, and we already know cos square omega t plus sine square omega t is 1. So you will get the answer as simply E0 square. So Ex square plus Ey square is equal to E0 square. It actually represents the equation of a circle. It actually represents the equation of a circle. So when we talk about circular polarization, the electromagnetic wave, it can have left hand circularly polarized, or it may be sometimes right hand circularly polarized. So whether it is left hand circularly polarized or right hand circularly polarized, that we mention depending upon the rotation of the electric field. If the electric field vector is oriented with the left hand thumb in the direction of propagation and the fingers curl in the rotation direction of the field with respect to time, then we call it as left hand circularly polarized. So we will take one example in this particular lecture and it will be clear to you. So let's verify whether this particular expression, whether the tip of this electric field vector, whether it actually defines a circular shape. So let's consider the case, that is E of 0 comma t is equal to E0 cos omega t Ax minus E0 sine omega t Ay cap. So just as we did it for the linear polarization case, here also we are going to consider different time instants ranging from 0 to the time period. So when t is equal to 0, omega t is 0. So just substitute here omega t as 0. So what is the answer? It is E0 cos 0 Ax minus E0 sin 0 Ay. So cos 0 is 1, whereas sin 0 is actually 0. So you will get the answer as E0 Ax. So how will you plot it in the graph? It means along x direction the amplitude is E0. So along x direction the amplitude value is going to be E0. So this is for at time t equal to 0. Next, let's consider the case t is equal to capital T by 8. At that time omega t is equal to pi by 4. So pi by 4 means it is 45 degree. So you will get the answer as electric field It is E0 by root 2 AX because cos pi by 4 is 1 by root 2 and sin pi by 4 is also 1 by root 2. So we'll get the answer as E0 by root 2 AX minus E0 by root 2 AY. So along x direction, E0 by root 2 and along y direction it is minus E0 by root 2. So it's going to be somewhere here. Now let's consider another time instant, that is t by 4, capital T by 4. When time is equal to 1 by 4th of the time period, omega t will be pi by 2. So substituting here omega t pi by 2, it is E0 cos pi by 2 ax minus E0 sin pi by 2. So cos pi by 2 is 0. So we will get the answer as minus E0 ay because sin pi by 2 is 1. So what does it mean? Along y direction, the magnitude is minus E0. So along y direction, the magnitude is minus E0. So at t equal to t by 4, this is a point where the electric field vector orients. Then similarly, you can consider the other two cases. When t is equal to half of the time period, omega t will be pi and the electric field value will be minus E0 AX. So where it is? This is x direction, magnitude minus E0. When it completes one time period, omega t will be 2 pi and the electric field value will be E0 AX. So if you consider another one point in between, that is 3t by 4, you will get the value as E0 AY cap. So when you plot it for the different time instance, see it is very clear from the picture, from the figure, that the tip of the electric field vector, it actually defines a circle. It defines a circle. And what about, see, when we move from t equal to 0, t by 8, t by 4, t by 2, 3t by 4, see it is actually in the clockwise direction. Okay, it is actually moving in clockwise direction. Okay, here I have represented the orientation, it is in clockwise direction. So this we got, and our assumption was the wave is traveling in positive z direction. Okay, so that is what I have noted here. The wave is traveling along z direction and it is in positive z direction. So that means here the z, it is out of the page. Okay, it is pointing out of the page. So just for you to understand whether this is right hand or left hand polarized. Okay, so what does it mean? So just check. See, wave is pointing outward. The wave is pointing outward. So taking your left hand and your thumb pointing out of the page and you're encircling your fingers, it actually matches with this particular figure, right? The wave is traveling out. That means your left hand pointing out towards you and encircling your fingers. It is same as the direction of this electric field in the clockwise direction. So it is actually matching with your left hand. So we can call it as left hand circularly polarized. So this particular example that we just talked about, it is an example for left hand circularly polarized. Another case is elliptical polarization. And the case is elliptical polarization. So a wave is said to be elliptically polarized if the electric field vector travels along an ellipse with variation in time. So what is the condition that should be satisfied for elliptical polarization? That is, the wave amplitudes along x and y direction, they must be unequal. That means Ex0 should not be equal to Ey0 and the phase difference, that is odd multiples of pi by 2. So this is a general expression for the electric field vector, that is E of z comma t is equal to Ex0 cos omega t minus beta z ax plus Ay0 cos omega t minus beta z plus phi p. So here let's consider n is equal to 0. If n is equal to 0, then the phase difference, it is pi by 2. So if phase difference is pi by 2 and considering the fixed point in space as z equal to 0, the electric field vector can be rewritten as E of 0 comma t is equal to Ex0 cos omega t ax minus Ay0 sin omega t ay. So why it is minus sign? Because cos omega t plus pi by 2 is minus sin pi omega t. So here let's say Ex0 cos omega t as Ex and Ey0 sin omega t as Ey. So this electric field vectors, we can also write it as Exax plus Eyay, where Ex is actually Ex0 cos omega t and Ey0 is equal to minus Ey0 sin omega t. So when you rearrange this expression and when you compute, you can find it Ex by Ex0 the all square plus Ey by Ey0 the all square is equal to 1. And this expression, it actually represents the equation of an ellipse. So just as we learned in circular polarization, elliptical polarization also, it has got two classified. It has got two classifications. One is the wave can be left hand elliptically polarized and the wave can also be right hand elliptically polarized. So whether it is left hand polarized or right hand polarized, that you have to check with the wave rotation and with the direction of propagation. If the wave rotation and the direction of propagation, if they are matching with your left hand, then it is going to be left hand elliptical polarization, and with the direction of propagation and the wave rotation, if they are matching with your right hand thumb and its fingers encircling, that you will call it as right hand elliptically polarized. So now let's see whether the tip of the electric field vector, whether it is actually defining an ellipse. Let's see. So same steps that we did it for linear polarization and circular polarization. So here we have the expression for the electric field vector, that is E of 0 comma t is equal to Ex0 cos omega t Ax minus Ey0 sin omega t Ay. So this is for the case when phase difference is pi by 2, that is n equal to 0. So here let's substitute for different time instance. When t is equal to 0, omega t is going to be 0. So substitute here omega t 0, what you will get? It is Ex0 cos 0 Ax minus Ey0 sin 0 Ay. That answer will be Ex0 Ax. So how to plot it in the graph? It's along x direction, the magnitude is Ex0. So now let's consider another time instant t by 8. That is omega t will be pi by 4. That means it's so cos pi by 4 1 by root 2, sin pi by 4 also 1 by root 2. So substituting that value, we get the electric field as Ex0 by root 2 Ax minus Ey0 by root 2 Ay. So that let's plot it in the graph. So along x direction it is Ex by root 2 and along y direction it is minus Ey by root 2. So let's say it is somewhere here. Now another time instant, 1 by 4th of the time period. When small t is equal to capital T by 4, omega t will be pi by 2. So cos pi by 2 is 0, whereas sin pi by 2 is 1. So substituting cos pi by 2 and sin pi by 2, you will get the answer of the electric field vector at z equal to 0 as minus Ey0 Ay. So how can you plot it in the graph? Along y direction, the magnitude is minus Ey0. So along y direction, magnitude is minus Ey0. Similarly, the another two time instance, 1 by half of the time period, omega t will be pi. So cos pi is minus 1, whereas sin pi is 0. So we'll get the answer as minus Ex0 Ax, minus Ex0 Ax. So how will you plot it in the graph? Along x direction, magnitude is minus Ex. Next case, t is equal to capital T. That means we completed one time period of the wave. So it is omega t will be 2 pi. You will get the answer as Ex0 Ax. So when you consider the different time instance, we are actually moving. See, from t equal to 0, t equal to t by 8, t by 4, t by 2, 3t by 4, etc. We are actually moving in clockwise direction. So in this particular example also, we are having clockwise rotation. Here, because we also assume the wave is actually propagating in positive z direction and z axis, it is out of the page. So this particular example that I just talked about, it is actually left hand elliptically polarized. So just take your left hand, see the thumb pointing out and encircling your fingers, it is actually matching with your left hand. Whereas if you try to match it with your right hand, will it match? No. Okay, your right hand thumb pointing towards you. But if your fingers encircling matching with this rotation, here it is clockwise, but your right hand fingers encircling, it is in anti-clockwise direction. So that is not matching. So this particular case that we explained right now, it is left hand elliptically polarized, or it is LHEP. So we can say, so there is, it's not a shortcut, but we can say if the rotation of the wave is clockwise, that means something like this. See, it is in clockwise direction. It is in clockwise direction. You to check whether it is clockwise or anti-clockwise, you have to consider for the different time instance. Okay, t0, t by 8, t by 4, t by 2, etc. You have to compute. So here when we computed, we understood we are moving from here and we are moving in the clockwise direction. Suppose if you substitute the values and if you're moving in an anti-clockwise direction, then this particular case, then if the rotation for this particular here, for this particular case, the rotation was clockwise, but whereas the same case, but the rotation in anti-clockwise direction, then it would have been a right hand elliptically polarized. So there is one shortcut that you can keep in mind, that if the wave propagates in positive z direction, that and the electric field rotation is clockwise, then it is going to be left hand polarized. Whereas if the wave is propagating in negative z direction and the wave and the electric field rotation, if that is clockwise, then it will be right hand polarization. So this you can use it for both circular polarization and elliptical polarization. So keep in mind this, I have said it for clockwise rotation. Okay, some rotation, something like this. So this case it was positive z direction, so that is why it is left hand polarized. Whereas if the wave was traveling in negative z direction, and clockwise rotation, then it would have been right hand polarized. So it is something like this, wave traveling negative z, that means it is into the page. That is what I have marked it as by the into sign. So your thumb pointing into the screen and rotating your right hand fingers, it is matching, so we can call it as, that will be right hand polarization. So now we just learned the theories, right? So now let's do some problem. So identify the polarization of the wave. It is given, first question, E is equal to 20 cos omega t minus beta z ax cap. So here we have only one component, only x component is present. So it is very clear, it is linearly polarized along x direction. Second question, 30 sine omega t minus beta x a z cap. But here, keep in mind, what it is given is magnetic field. What is polarization? That is the orientation of electric field vector. So what you have to do here first? First you have to compute electric field expression. So the direction of wave propagation is AX, x direction, whereas the magnetic field is along z direction. So magnetic field is along z direction, wave is propagating along x direction. You will get to know the electric field is along y direction. So how can you write the electric field vector in terms of magnetic field? That is going to be E is actually, its amplitude will be h0 by eta in terms of intrinsic impedance. So E is equal to 30 by eta sine omega t minus beta x, and what is the orientation of electric field? Y it should be. So it is AY cap. So here we understood the electric field intensity vector, it has only one component and that is along y direction. So we can say it is an example for linearly polarized station. And this one is linearly polarized along y direction. So let's consider the third case, that is C. E is equal to 25 sine omega t minus beta x ay cap plus 30 cos omega t minus beta x az cap. So here the electric field, it has got two components. So the answer, it should be either circularly polarized or elliptically polarized. But now let's look at the amplitude. Okay, one amplitude is 25 and another amplitude is 30. That means the amplitudes are unequal. And another, see, one side it is sine and another side it is cos. So sine and cos, the phase shift is pi by 2. So there is a phase shift of pi by 2 and amplitudes unequal. So it is clear it is going to be elliptically polarized. But whether it is left hand polarized or right hand polarized, in order to understand that, you have to substitute for different time instance. Okay, you have to substitute the value for different time instance, just as we did it before, that you have to substitute for t equal to 0, t equal to t by 8, or omega t pi by 2, omega t pi, something like that you have to substitute. So when you substitute it, just okay, for let's consider the first case. When t is equal to 0, okay, when t is equal to 0, what answer you will get? This first term will be 0 because sine 0 is 0. Then you will get only the second term, that it will be 30 cos AZ cap. So here we have 30. So along Z direction it is 30. So horizontal it is Y and vertical it is Z. So it is 30 AZ cap. Then when omega t will be pi by 2, you will get the answer as 25 AY cap. So along Y direction the magnitude 25. So similarly, when you substitute for omega t is equal to pi, you will get the answer as minus 30 AZ cap. So along Z direction minus 30. Then the another case was 3t by 4. So that there you will get it as minus 25. So that is minus 25. So just see what about the rotation? What about the rotation? Yes, it is having a clockwise rotation and the wave is along positive direction, right? It is along positive x. So it is in positive direction and clockwise rotation. So we will get to know it is left hand elliptically polarized. So here I have given some homeworks, as it's not homework actually because I've already given you the answer, but do take some time, work out and check whether the answers that I've provided is correct or not. Okay, so please do work out all these problems, and I have already given the answers for your understanding. If you're stuck at some point, do check these answers and be clear with the concept of polarization. So for this particular lecture, I have referred the textbook Engineering Electromagnetics authored by W.H. Heath. You may also refer the textbook authored by Matthew N.O. Sadiko. In this lecture, we learned about polarization of electromagnetic wave. So polarization of electromagnetic wave, it is actually the orientation of electric field vector at a fixed point in space. And it is of three types: linear polarization, circular polarization, and elliptical polarization. Thank you. Thank you so much for your patient listening.